Alright, here's our lesson on section 4.2, inverse functions. Let's do a little warm-up. I want you guys to try these 4 questions in your notebook, and then you can restart the video. Seriously, try them. Okay, now you've tried them. So this set of ordered pairs here, we've got 1, 3, 2, 3, negative 1, 2. Well, what we've always said is that two x values can have the same y value, but every x value can only have one y value. So that makes our first ordered pair here a function. Alright. Where is the function f of x squared, f of x equals x squared increasing, and where is it decreasing? So again, we draw our function here, and x squared is a parabola pointing up. Okay? And if we read left to right, start on the left side, and we read left to right, well, we're decreasing on this side, and we're increasing on this side, so the interval that we're increasing is going to be 0 to infinity. Okay? These are our x values of increase. And then decreasing is going to be on this side. We're coming down here. So we're going to be coming from negative infinity in the x to 0. Oops. Need to have parentheses, not brackets, around the infinity, because we can't really include infinity. And so this is decreasing. Alright. And then domain. We have x plus 5 over x squared plus 3x minus 18. Well, I'm going to set my denominator equal to 0 and solve. So I get x plus 6 times x minus 3 equals 0. And so I get x equals negative 6 or 3, which means our domain is all x's provided that x doesn't equal negative 6 or 3. Okay? And then number 4 here, I'd just like you to write down what you think a one-to-one function is. What do you think that means? Okay. We'll come back to this later. But give your best guess. Right. You might look it up and try to infer, and we'll talk about it some more. Okay, we want to determine if a function is one-to-one. Our other goals are to determine the inverse of a function from a map or ordered pairs, and then we want to graph the inverse given the graph of a function. So we'll be given like a picture of a function, you know, something happening, and we should be able to graph the inverse of that once we know what we're doing here. And then we want to find the inverse of a function defined by an equation. So there's a whole process for that, and we're going to go through that as well. Alright. So first of all, a one-to-one function. Okay, so a one-to-one function is a function that has for every input one output, and every output has one input. So before, a function can be a function and not be one-to-one, meaning that one x value can have two y's, like in a parabola. Okay? Parabola, negative 3 and 3 are going to have the same y value. But a one-to-one function would not, that would not happen in a one-to-one function. So a parabola by itself is not a one-to-one function. And so looking at our first example here, we can see that 55 and 61 both have an output of 38. So because two inputs have the same output, we would say not a one-to-one. Okay. But then we come over here and we have 2, negative 1, 0, 1, 2, and all of them have different outputs. So yes, one-to-one function. Another way to think about it is, if I found the inverse of the original function, would the inverse also be a function? If it is, then we say it's a one-to-one function. Okay. So we want to find the inverse now. Okay, so using a horizontal line test, we can determine if a graph is a function, or excuse me, a one-to-one function, and then know if the inverse is a function as well. Okay. So f of x equals x squared, parabola, and then we draw a horizontal line. X cubed, something like that, and we draw a horizontal line. Now, I'm going to tell you that f of x cubed is, yes, a one-to-one, and x squared is not. Well, what do you notice? What's the big difference between the two? Hopefully you guessed that in our one-to-one function, we only hit that horizontal line one time. Whereas in our non-one-to-one function, our parabola here, we hit it twice. So similarly, they're both functions, because if we did the vertical line test, we would only hit one time. But because the horizontal line hits it twice, our x squared is not one-to-one. Okay, so that means that its inverse would not be a function. Alright, so now we want to find the inverse given a map, or you could even say ordered pairs. It's almost like they're ordered pairs here. But it's fairly straightforward. We see that our states are here originally as the inputs, and population is the output. And you notice that each input has its own output. And if we reverse and make population go first, population becomes the input, and our state becomes the output, well then this is our inverse. If this is f of x up here, then this is f inverse of x down here. So for a map, or for ordered pairs, f of x will be x comma y, and then to make it the inverse, you swap the inputs and the outputs. Y comma x. And that creates your inverse function. Alright. So we want to find the inverse from a set of ordered pairs. So we want to see if this guy is a one-to-one function. So we look at all of the inputs, and then we look at all the outputs. Each input has its own output. Nothing ever doubles up, and no outputs ever double up. They're all unique. So yeah, it's a one-to-one function. Then we want to find the inverse. So I'm just going to list. First point was -3, -27, so now we have -27, -3. Then we have -8, -2, -1, -1, 0, 0, 1, 1, oops, 2, 8, and 3, 27. Okay? Then we want to verify that two functions are inverses of each other. So we need to make composites of each. And this is what I had asked you guys to look up a little bit, the composite function. So in order to verify, if they're telling me verify two are inverses, then I'm going to do this. I'm going to say, well, I have f of my inverse function. Or in this case, f of cubed root of x. Because this was my inverse function. So I'm plugging it into where I see x. So I'm going to do the same thing here. So that's going to equal something cubed. Well, the something that's cubed is my inverse function, cube root of x. And what do I get out of that? Well, I get x out. Then I got to go in reverse, and I say f inverse of f of x. So I make composites. So I have f inverse of x cubed. So I'm going to take the cube root of x cubed, which is x. So because both answers yield just an x, they simplify down to the identity function, which is f of x equals x. Then we say that we have proven that they are inverses. So when you make both composite functions here, and their final answer simplified is x, then you've proven that they were inverses of each other to begin with. Another way to look at it too is if I put, say, if I did 8, if I did the, let's see, if I did f inverse of 8, I would get the cube root of 8, which is 2. Now if I take that 2 and I plug it back into f of x, so 2 cubed is equal to 8. If I get back here to where I started from with my inverse, then I've proven they're inverses as well. And you could go backwards. You could say, what is f of 2? Well, f of 2 would be 8. And then go, what's f inverse of 8? Well, that's 2. So you get back to where you started, so they're inverses of each other. Okay, I want you guys to give these a try. They're a little more complicated, but again, I'm gonna give you a starting point. We're gonna say f of f inverse of x. So we're gonna be plugging this whole nugget right in here. So we have f of 1 over x plus 1. Alright? So I want you to take it from there. Okay, so hopefully you attempted this and you see that my f of x is 1 over something minus 1, right? That's what we use to represent, something, the x, the variable. Not sure what it is, but we could change it. It could mean something. In this case, it means our inverse function, 1 over x plus 1. So here we end up with this equaling 1 over x plus 1 minus 1, which equals 1 over x, which then you have to multiply 1 times x over 1, the reciprocal, which is just x. And then we do the exact opposite, f inverse of f of x, and we get f of 1 over x minus 1. So we end up with 1 over x minus 1 plus 1. So again, we flip this and multiply, so we end up with x minus 1 plus 1, which equals x. So because both composite functions create the value of x, then we've proven that we have verified that they are inverses. Alright, so graphing an inverse. So we see this is our function here, our f of x, this line that's created by these points. Okay? If we were to mirror them, as we're doing right here, we're going to mirror across this line. And this line is the equation y equals x. That's the identity function. So if you're mirroring across that, you create the inverse. And practically what we're doing is we're taking whatever the x and y values are here and we're just flipping them. So this guy's x and y was, his x was negative 2, positive 4. So to flip it, we make it positive 4, negative 2, and we create that point. That's what it's telling you to do. you're mirroring each point across diagonally this identity function here to create our inverse function. Oops. So there you go. And that becomes f inverse of x. Alright, so what I want you to do is take a minute and do a little journal entry on what you see happening here in your own words. Okay? It's really important that they're in your own words, because just trying to memorize what I said isn't going to do you any good. You have to really process it in your own way. Alright, so we want to graph the inverse here. So first thing I'm going to do is I am going to show you guys the identity function. So again, it's this dashed line where y equals x, and we need to figure out some points. So we've got this starting point here, and we got another point here, and I'd say another point here. That works. And maybe we'll do, I don't know, we'll try this one as well. Alright, so this point here is -1, 1. This point here is 0, 2. This point here looks to be about 2, comma, 2 2/3. So that's going to be 8/3. And then this point here is 3, comma, 3. Alright. So in red, I'm gonna plot my inverse points. So we have 1, -1, the inverse of this guy. Then we have 2, 0, the inverse of this guy. Then we have 8/3, so 2 2/3, comma, 2. So right around there. And then 3, 3, so we just go right over the top with 3, 3 there. Our graph comes through, and now we have our f inverse of x. And you could list some points of that. You could say 1, -1 was a point, 2, 0 was a point, 8/3, comma, 2 was a point, and then our last one was 3, 3. Oops, not 3/3, but 3, comma, 3. Alright, so this is my f inverse of x. Now my domain would be all values to the right of 1, because you see this arrow, it would keep going on. So my new domain of this is all x's provided that x is greater than or equal to 1. And my new range is y greater than or equal to -1, because there's no y values that are going to be down here. They're only going to be above that point there. So here's an important fact for our inverses. The domain of our original function is the range of our inverse, and vice versa. The range of f of x is the domain of f inverse of x. So we can call this the range of f of x, and we can call this the domain of f of x. So they just swap. Alright, so if I were to give you the domain and range, you should be able to tell me automatically what the inverse's domain and range are as well. Alright, so our last goal was to find the inverse of a function given an equation. Okay, so our first step is always to write y equals the terms of x. So you want everything set equal to y and involving x on one side. Alright, and then we want to switch positions of the y and the x. Alright, wherever you see an x, that becomes a y. Wherever you see the y, that becomes an x. Alright, then we solve for y. And then we want to check that they're inverses by showing the composites equal x. Okay? So for this first one here, we have f of x equals 2x plus 1 over x minus 1. So I write it as y equals all of my x's. And then everywhere that I saw an x, I'm placing y's. So there was an x in top and bottom, so now there's a y in top and bottom with an x right there. And then our goal is to now solve for y. So see what you think. Give it a try. It's kind of a tougher problem, but let's, on the next slide, I'll finish it for you. So pause it, give it a shot, see if you can simplify it down to solve for y. And remember, you can always test it by going and making composites of your final with your original. If you end up with x, you're good to go. Okay, so here is the function as we saw it, moving on to step 4. And so, first thing I'm going to do is I'm going to multiply both sides by y minus 1 so that I get rid of it here and that everything moves into the numerator. So I have y minus 1 times x equals 2y plus 1. And then I want to distribute through. I end up with xy minus x equals 2y plus 1. Now I'm going to subtract 2y over, and I'm going to add x over. So first things first, let's go xy minus 2y minus x equals 1. And then I'm going to add x to both sides. And what I'm doing is I'm trying to solve for y, so I'm moving all things involving y to one side and all things that don't have a y to the other. So we can bring this up here and say we have xy minus 2y equals x plus 1. Alright, and now this is a classic algebra move where we're going to factor out the variable we want and divide away the rest. So we factor out y, leaving x minus 2 equals x plus 1. Then we're going to divide away x minus 2. Divide away x minus 2. So then y equals x plus 1 over x minus 2. This then is our f inverse of x equals that guy. And you can prove that by creating a composite function of our original function with our new function here. Okay, so we want to find the domain and range of a function without graphing. Of our inverse function. So that's all we're trying to do here. So first things first is I want to look at this and say, well, what is my domain? Again, in domain, all we're looking at is, can we ever divide by 0? And can we ever square root a negative? Because if anything makes us do that, then it can't be in our domain. And so for this problem here, there's no square roots, but there is an x minus 1. So I'm going to set my denominator equal to 0 and x equals 1. So my domain is x provided that x can't equal 1. Alright? And then this is a rational function with a vertical asymptote at 1. Okay? X equals 1. And then because the powers are the same, y equals 2 is our horizontal asymptote. So I know that my range is going to be y provided that y can't equal 2. Alright? So if this is the domain of my original function and this is the range of my original function, then to get the domain of f inverse, I just switch. So I'm going to have x provided that x doesn't equal 2, and my range of f inverse is just going to be y provided that y doesn't equal 1. Another way you could think about it is if you find the inverse of your function here, like we did in our, this is the same function that we found our inverse in before, where we had f inverse of x is equal to x plus 1, plus 1 over x minus 2. Well, now I can say that the domain of my inverse is x provided that x doesn't equal 2, which is what we saw here, right? And then we could also say, well, I know my domain there, so my range in my original function is right here. So if you find your inverse, find the domain of your inverse, then you know the range of your original function. And the domain of your original function becomes the range of your inverse. So finding the inverse function can help you find your range of your original function. All right? Okay. So we want to find the inverse of a function that isn't one-to-one. We need to restrict it. And what do I mean by that? We need to restrict the domain of the original function so that we're only looking at a certain part of that function. And so we said before, if we drew a horizontal line, like all these grid lines, these horizontal grid lines, they would hit it twice everywhere we go. So what we need to do is eliminate the part of the graph that makes us hit it a second time. Okay, so we can either eliminate this half or we can eliminate this half. I'm going to start by eliminating the left half. Okay, and so do that in green here. So we're going to ignore this half. Well, this half only happens when x is less than 0. So what we're going to say is that we have f of x equals x squared, provided that x is greater than or equal to 0. So it can't be less than or equal to 0. So if we were to solve for the inverse here, we get y equals x squared. So x equals y squared. So then x equals, or excuse me, y equals the square root of x plus or minus. But again, if we have plus or minus, well, x is not going to be greater than 0. So our only one we can look at is y equal to positive root x. And that's going to be this top half here of the function. So if we were to draw that, it goes back to our square root function. We're at 0, 0, 1, 1, 4, 2. And there's our function. This represents y equals the positive root x. Okay? You could also say that we have a second function, two functions. Y equals negative root x. Okay? And that would represent the original function of f of x equals x squared, provided that x is less than or equal to 0. Okay? So those are the two options. That's how you restrict domain to only look at a one-to-one function. Alright? Alright, so here's number 49 from your textbook as a little bonus for you guys. Alright? 49 here, we have f of x equals 4x plus 2. And they ask us to, they tell us that it's a one-to-one function, and they say find the inverse and check your answer. State the domain and the range of your original function f and f inverse. Graph them both and put y equals x, all on the same coordinate plane. So y equals 4x plus 2. So then x equals 4y plus 2. We have x minus 2 equals 4y. And then y equals 1/4 x minus 1/2. Alright? So then that would be my f inverse of x equals a fourth x minus a half. So we want to check our answer. So we're going to say f of 1/4 x minus a half, or 4 times 1/4 x minus a half plus 2. So that equals x minus 2 plus 2, which equals x. Check. Then we got to do the other way. F inverse of 4x plus 2, so equals a fourth times 4x plus 2 minus a half. So we end up with x plus a half minus a half, which equals x. Check. So we've proven. This is our check here. And then we want to graph the 2 plus y equals x after we state our domain and range. So our domain for this function, there's no square root and there's no dividing by 0, so our domain is all real, which means that the range of your, so we have domain, we have range, and then we have domain of our f inverse and range of f inverse. So because this is all real, we know that this is all real. There, they match. Then we look at our inverse function. Our inverse function here should have a domain. Let's see, no square roots, no dividing by 0, so it should be all real. So the range of the original function is also all real. Alright, and lastly we want to graph this. So first they ask us to graph y equals x. So I'm going to put 4, 5, 6. I'll do a few more. Okay, so y equals x goes like this. Alright, and then our original function I'll put in blue, and our original function was 4x plus 2, so we're going to have a y-intercept at 2. Ask yourself, what kind of function is this? Yeah, it's linear. Okay, we have intercept at 0, 2, and a slope of 4. So I'm going to go up 1, 2, 3, 4 over 2. Okay, and we draw our line. Alright, so this is f of x. And you might go down, 1, 2, 3, 4, and over 1, 2. Something like that. So you've got 3 points to work with here. So my inverse function is going to be the inverse of those. So instead of 2 comma 6, I'm going to have 6, 1, 2, 3, 4, 5, 6, comma 2. And then instead of 0, 2, we're going to have 2, 0. Instead of negative 2, negative 2, oh, we get negative 2, negative 2. And so there's our f inverse graph. Alright. Hope that helped. See you guys on Monday.